A toy car slows to a stop, so you remove its battery and call it dead. Yet the same cell may run a clock. The battery was never a simple bucket that changes instantly from full to empty. Its chemistry provides an electromotive force, while the materials inside also create an internal electrical resistance. A useful circuit model places that internal resistance in series with an ideal voltage source. When a device draws current, some voltage is lost inside the battery before the remaining terminal voltage reaches the device. The relationship is compact. Terminal voltage equals the source voltage minus current multiplied by internal resistance. As an alkaline or zinc-carbon cell is discharged, reaction products accumulate, and transport inside the cell becomes less effective. Its internal resistance rises, so a large current produces a larger voltage drop and more heating inside the cell. A motorized toy demands bursts of relatively high current to overcome friction, accelerate gears, and produce mechanical torque. Under that heavy load, the old battery's terminal voltage can collapse below the toy's minimum operating level. The toy stops even though the cell still contains some chemically available energy. A quartz clock uses tiny pulses of current and has a much larger effective load resistance than the motor. Because the clock's current is small, the same internal resistance causes only a small voltage loss. The terminal voltage may remain above the clock circuit's lower cutoff, allowing the hands to advance for days or weeks. After a battery rests, its open circuit voltage can rebound slightly as concentration gradients inside the cell relax. That recovery can help a light load temporarily, but it does not recreate the capacity already consumed. Different devices also have different electronic cutoff thresholds, so one device may reject a cell that another accepts. Temperature changes reaction speed and internal resistance, which is why a cold battery often performs worse under load. The remaining energy is real, but it is low-quality power, available slowly, not at the high rate the toy needs. Reusing a sound cell in a non-critical low-drain device can extract more of that remaining energy, but failure may be unpredictable. Never reuse a cell that leaks, swells, corrodes, overheats, or has damaged insulation. Do not mix old and new cells in one device, because unequal cells can drive one another into leakage or reverse voltage. When the clock finally stops, remove the battery promptly and follow local recycling or disposal rules. The old cell works again only because the clock asks for less current, not because the battery has somehow recharged itself.